Hi friends, welcome back to our series of sessions on industrial and process instrumentation. Today we shall discuss about properties of liquid fuels. The various types of fuels like liquid, solid and gaseous fuels are available for firing in boilers, furnaces and other combustion equipment. The selection of the right type of fuel depends on various factors such as availability, storage, handling, pollution and landed cost of the fuel. The knowledge of the fuel properties helps in selecting the right fuel for the right purpose and efficient use of the fuel. The following characteristics determined by laboratory tests are generally used for assessing the nature and quality of fuels. Let's discuss today about the properties of liquid fuels. Liquid fuels like furnace oil and LSHS. LSHS stands for low sulfur high stack, are predominantly used in industrial application. The first property is the density, which is defined as the ratio of the mass of the fuel to the volume of the fuel at a reference temperature of 15 degrees centigrade. Density is measured by an instrument called hydrometer. The knowledge of density is useful for quantity calculations and assessing ignition quality. The unit of density is kg per meter cube. Next point is specific gravity. This is defined as the ratio of the weight of a given volume of oil to the weight of the same volume of water at a given temperature. The density of fuel relative to water is called specific gravity. The specific gravity of water is defined as 1. Since specific gravity is a ratio, it has no units. The measurement of specific gravity is generally made by hydrometer. If we see the specific gravity used in calculations involving weights and volumes of different fuels, for furnace oil, for water it is 1, for light diesel oil it varies from 0.85 to 0.87, for furnace oil it varies from 0.89 to 0.95, and for low sulfur high stock it varies from 0.88 to 0.98. So the next factor is the viscosity. The viscosity of a fluid is a measure of its internal resistance to flow. Viscosity depends on the temperature and decreases as the temperature increases. Any numerical value for viscosity has no meaning unless the temperature is also specified. Viscosity is measured in Stokes or centistokes. Sometimes viscosity is also quoted in England. The measurement of viscosity is made with an instrument called viscometer. Viscosity is the most important characteristic in storage and use of fuel oil. It influences the degree of preheat required for handling, storage, and satisfactory atomization. If the oil is too viscous, it may become difficult to pump, hard to light the burner, and tough to operate. Poor atomization may result in the formation of carbon deposits in the burner tips or on the walls. Therefore, preheating is necessary for proper atomization. So the next point is flash point. The flash point of a fuel is the lowest temperature at which the fuel can be heated so that the vapor gives off flashes momentarily when an open flame is passed over it. Flash point for furnace oil is typically at 60 degrees centigrade. Next is pour point of a fuel, which is the lowest temperature at which it will pour to flow when cooled under prescribed conditions. It is a very rough indication of the lowest temperature at which fuel oil is readily pumpable. Next one is specific heat, which is the amount of heat in kilocalories needed to raise the temperature of 1 kg of oil by 1 degree centigrade. The unit of specific heat is 1 kilocalorie per kg degree centigrade. It varies from 0.22 to 0.28 depending on the oil's specific gravity. The specific heat determines how much steam or electrical energy it takes to heat oil to a desired temperature. Light oils have a low specific heat, whereas heavier oils have a higher specific heat. That's the thumb rule, which is normally followed in industry. So the next point is calorific value, which is the measurement of heat or energy produced and is measured either as gross calorific value or net calorific value. The difference being the latent heat of condensation of the water vapor produced during the combustion process. Gross calorific value assumes all vapor produced during the combustion process is fully condensed. Net calorific value assumes the water leaves the with the combustion products without fully being condensed. Fuel should be compared based on the net calorific value. The calorific value of coal varies considerably depending on the ash, moisture content, and the type of coal, while calorific value of fuel oils are much more consistent. The typical gross calorific values of some of the commonly used fuels are, for fuel oil, the gross calorific value in kilocalories per kg, kerosene 11,100 kilocalorie per kg, diesel oil 10,800 kilocalories per kg, light diesel oil 10,700 kilocalories per kg, furnace oil 10,500, and low sulfur high stock 10,600 kilocalories per kg. Then it is this sulfur content. The amount of sulfur in the fuel oil depends mainly on the source of the crude oil and to a lesser extent on the refining process. The normal sulfur content for the residual fuel oil, which is normally called as furnace oil, is of the order of 2 to 4%. Typical figures are kerosene as a percentage of sulfur 0.05 to 0.2, then diesel oil it will be 0.05 to 0.25, light diesel oil 0.5 to 1.8, furnace oil 2 to 4, and low sulfur high stock is less than 0.5. The main disadvantage of sulfur is the risk of corrosion by sulfuric acid formed during and after combustion and condensing in cool parts of the chimney or stack, air preheater, and economizer. Next point is ash content. The ash value is related to the inorganic material in the fuel oil. The ash levels of distillate fuels are negligible. Residual fuels have more of the ash-forming constituents. These salts may be compounds of sodium, vanadium, calcium, magnesium, silicon, iron, aluminum, nickel, etc. Typically, the ash value is in the range of 0.03 to 0.07%. Excessive ash in liquid fuels can cause fouling deposits in the combustion equipment. Ash has erosive effect on the burner tips, causes damage to the refractories at high temperatures, and gives rise to high temperature corrosion and fouling equipment. Then is the carbon residue, which indicates the tendency of oil to deposit a carbonaceous solid residue on a hot surface, such as a burner or injection nozzle. When its vaporizable constituents evaporate, residual oil contain carbon residue ranging from 1% or more. Then water content of a furnace oil when supplied is normally very low as the product at refinery site is handled hot and maximum limit of 1% specified in the standard. Water may be present in free or emulsified form and can damage to the inside furnace surfaces during combustion, especially if it contains dissolved solids. Then is the storage of fuel oil. It can be potentially hazardous to store furnace oil in barrels. A better practice is to store it in cylindrical tanks, either above or below the ground. Furnace oil that is delivered may contain dust, water, and other contaminants. The sizing of the storage tank facility is very important. A recommended storage estimate is to provide for at least 10 days of normal consumption. Industrial heating fuel storage tanks are generally vertical mild steel tanks mounted above the ground. It is prudent for safety and environmental reasons to build bound walls around tanks to contain accidental spillages. Loss of even one drop of oil every second can cost you over 4,000 liters a year on a rough estimate. Then the removal of contaminants. Water content we have seen. Then you see the typical specification of fuel oils. Density is around 0.89 to 0.95, LSHS 0.88 to 0.98, LDO 0.85 to 0.87. Density, how it varies, whether it is for flash point, 66 for furnace oil, 93 degrees centigrade, and 66 degrees for light diesel oil. 4.20 degrees centigrade, 72 degrees centigrade, and 18 degrees centigrade. Gross calorific value in kilocalories per kg we have already seen. And sediment as a percentage of weight is 0.25 in furnace oil, 0.25 in LSHS, 0.1 in light diesel oil. So percentage of total sulfur is up to 4 in furnace oil, 0.5 in LSHS, and 1.8 in light diesel oil. Water content as a percentage of volume, 1% in LSHS and furnace oil and 0.25% in light diesel oil. And as a percentage of weight, 0.1% in furnace oil, 0.1% in LSHS, and 0.02% in light diesel oil. Then we have removal of contaminants. Furnace oil arrives at the factory site either in tank lorries, by road, or by rail. Oil is then decanted into the main storage tank. To prevent contaminants such as rags, cotton waste, loose nuts or bolts, or screws entering the system and damaging the pump, coarse container of 10 mesh size, which is not more than 3 holes per linear inch, is positioned on the entry pipe to the storage tank. Progressively, finer strainers should be provided at various points in the oil supply system to filter away finer contaminants such as external dust and dirt, sludge and free carbon. It is advisable to provide these filters in duplicate to enable one filter to be cleaned while other oil supply is maintained through the filter. Then we have the pumping. Heavy fuel oils are best pumped using positive displacement pumps as they are able to get fuel moving when it is cold. A circulation gear pump running on LDO should give between 7,000 to 10,000 hours of service. Diaphragm pumps have a shorter service life but are easier and less expensive to repair. The centrifugal pump is not recommended because as the oil viscosity increases, the efficiency of the pump drops sharply and the horsepower required increases. Light fuels are best pumped with centrifugal pumps. When higher pressures are required, piston or diaphragm pumps should be used. Then let's see the storage temperature and pumping temperature. The viscosity of furnace oil and LSHS increases with decrease in temperature, which makes it difficult to pump the oil. At low ambient temperatures, that is below 25 degrees centigrade, furnace oil is not easily pumpable. To circumvent this, preheating of oil is accomplished in two ways. The entire tank may be preheated. In this form of bulk heating, steam coils are placed at the bottom of the tank, which is fully insulated. And B, the oil can be heated as it flows out with an outflow heater. To reduce steam requirements, it is advisable to insulate tanks where bulk heating is used. Bulk heating may be necessary if flow rates are high enough to make outflow heaters of adequate capacity impractical, or when the fuel such as LSHS is used. Thermostatic temperature control of the oil is necessary to prevent overheating, especially when oil flow is reduced or stopped. This is particularly important for electric heaters since oil may get carbonized when there is no flow and the heater is on. Thermostat should be provided at a region where the oil flows freely into the suction pipe. The temperature at which oil can readily be pumped depends on the grade of the oil being handled. Oil should never be stored at a temperature above that necessary for pumping, as this leads to higher energy consumption. So those are all the points of properties of liquid fuels for discussion today. Hope you have enjoyed the session. Let's meet in the another session.